Hi, welcome back. Just like what we did with continuous time Fourier series, we can apply properties of the discrete time Fourier series to help us calculate quickly the Fourier series of discrete time signals that are related to basic shapes and basic mathematical formulas whose Fourier series we already know. So let's take a look at some of those properties today. And they're mostly the same or very similar to continuous time Fourier series. And I just want to point out some important differences. But again, we're not going to look at these in as much detail as we did with the continuous time Fourier series because we already, we saw those gory details in the continuous time Fourier series. Okay, so the first one I want to mention is the multiplication property. And it says that suppose xn is periodic with period n and has Fourier series ak, and yn is also periodic with period n and has Fourier series coefficients bk. Now suppose we have a new signal that is the multiplication of x with y, and we want to know what is its Fourier series, or what are its Fourier series coefficients. Well, it turns out that the Fourier series is what's called the periodic convolution of the AKs with the BKs. So I'm going to write this like this. Now, first of all, let's recall what convolution is. It's taking the two series, expressing them versus a dummy variable, and we're calling that dummy variable L here, flipping one of them, okay, which is the B, so that's why there's a minus L, and then shifting it by the independent variable, which is K, then adding over that dummy variable L. Now, in regular convolution, you sum from minus infinity to infinity. This is called the periodic convolution, and we're only summing over one period. So it's actually simpler than regular convolution because the sum is finite. So that is the multiplication property. The Fourier series coefficients of two signals multiplied together are the periodic convolution of the two Fourier series. Okay, next is the time shift property, and it's actually the same as in continuous time, but we need it for the next one, which is the first difference. So this says that if x of n is periodic with period n and has Fourier series coefficients ak, then x of n minus n0, where n0 is a constant, has Fourier series coefficients ak, the original ones, times e to the minus jk omega 0 n0, where omega 0 is the usual 2 pi over n. So remember, we saw this for continuous time. E to the minus jk omega 0 n0 has a magnitude of 1, and so this time shift is not changing the magnitude of the Fourier series coefficients, it's just changing their phase, which is what we expect when we shift a signal in time. So that's the time shift property. Now, first difference is the one that I really want to talk about. We need the time shift property for the first difference. There's no differentiation property in discrete time because that's a continuous, taking the derivative is a continuous operation. It's a limiting operation. And in discrete time, what we do is we take a first difference. So suppose x of n has Fourier series coefficients ak and is periodic with period n. We might have a signal yn, or that's the first difference of x of n. We talked about the first difference a while back. So we want to know what are its Fourier series coefficients. Well, something that I haven't talked about yet is linearity. And linearity still applies. I'm just not going to go over it because it's what you would expect. Linearity allows us to take the Fourier series of each piece. So the Fourier series of x of n is what we're saying is ak minus then the Fourier series coefficients of x delayed by 1 unit. Well, that's a time shift property with n0 being 1. So I have this. And I can factor out the ak if I like. And that is again, this is the Fourier series coefficients of xn minus 1. And that is the first difference property. Okay, so those are the ones that I want to point out to you right now. There are others. There are frequency shifting. There's the linearity, which I didn't write up here, but it still applies. There's time scaling. Okay, I just don't want to take the time to talk about those because they're very similar to what we did in continuous time. Now, reference materials, like textbooks, will often have tables that for your convenience. So here's a table 3.2 in Oppenheim's Signals and Systems 2nd edition textbook. And you should be familiar with these properties. So here's linearity. Actually, before that, we've got suppose xn is periodic with period n and has Fourier series coefficients ak, and yn has Fourier series coefficients bk. So here's the linearity property, right? Some constant times x plus some constant times y has Fourier series coefficients, that constant times a plus that constant times b. Meaning you can take it piece by piece. Here's the time shifting property, which we just derived now. X, n minus n0, has Fourier series coefficients ak e to the minus jk, and in parentheses there is omega 0, 2 pi over n, n0. Frequency shifting, conjugation, these are all the same as what we saw in continuous time. Time reversal. Time scaling is a little different, but I'll let you look at that on your own. And then there's this duality that exists. We just talked about the multiplication. The multiplication of two signals has Fourier series coefficients, which is the convolution of the two Fourier series. And then if you convolve in time, the convolution of two signals has Fourier series coefficients that are the multiplication. So that's the duality there. Here's the first difference, which we derived, right? ak times 1 minus e to the minus jk omega 0. And there's a running sum, which is analogous to an integrator in continuous time. And there are these symmetrical properties, which are the same as continuous time. And Parseval's relation is very similar as in continuous time. The n's the t's are replaced by n's, and the sums take the place of the integrals. And everything changes as you would expect. So in the next video, or the next couple videos, what I want to do is practice applying these properties so you can see how we can calculate, or we can use these properties to our advantage to calculate the Fourier series coefficients of signals that are related to signals whose Fourier series we've already calculated. Okay, so I'll see you in the next video.